All right, so what I'm going to focus on in this video for section 7.3 is really just the one step in the hypothesis test that will be different when you need to run a t-test. So let's review first how you know when you need to use a t-test rather than z, rather than the standard normal. And this is the same way that we made the choice for the confidence intervals. So the key thing to note here is that when you do not know sigma, remember sigma is the standard deviation for the whole population. When you do not know sigma, basically what that means is you only have the sample standard deviation. Right? Sigma is the standard deviation for the whole population. S is just for a sample. So if you don't know sigma, that is when you switch and you use a t distribution rather than the standard normal z. Okay, but what I want you to realize is that beyond that one step of finding the rejection region and the critical values, everything else will be done exactly the same for these tests in 7.3 as it was in section 7.2. Okay, all the other 4 steps are going to be done the exact same way. All right, so again, what I'm going to focus on with you here is mainly just making sure that we're clear on how to find t-values instead of z. So the basic format's going to be the same. You will look at the type of test from the alternative hypothesis. And if you are looking at a situation where you do not know sigma, you're going to use a t-curve. It's still bell-shaped. It's still centered at 0. It's just a little bit wider, technically, than the standard normal. Now, just like for z, the type of test, the left tail will tell you where to shade the rejection region. The main difference here is going to be reading the table for the t distribution. So you're going to go to your t table, which looks like this, and I have linked this for you on the course homepage, with 2 things. All right, one will be your level of significance. Remember that alpha is the given level of significance for the test. But you're going to have a new parameter here as well, which is called the degrees of freedom. And when you're working with the means like we are, the degrees of freedom will always be n minus 1, where remember n is the number of values in your sample. All right, so for this particular test, I have a level of significance at 0.05, and notice this would be considered a one-tail alpha because it's all shaded on one side of the curve. And then if my sample size is 9, then I'm going to subtract 1 from that, and I'm going to use 8 degrees of freedom. Okay, and that's all there is to it. So when I go to my table, my t-table, I'm going to look this up as a one-tail alpha. One tail goes for left or right, and that level of significance was 0.05. And then we said to use 8 degrees of freedom, and that's going to show me a critical value of 1.860. Now, the one thing you will have to note about using the t-table is that it only gives you positive values. So you will have to remember, if you have a left-tailed test, then your critical value is always going to be negative. And you'll see that if you do a sketch. So critical value here would be negative 1.860 because it is a left-tailed test. Now, just like I told you for Z, I like to do my rejection regions with a sketch, but if you're asked to kind of write this out, just like we did before, the critical value is what you get from the table. We're going to call this T sub 0 because it's from a T distribution, and that would be negative 1.860, again negative because it's a left-tailed test. And then the rejection region would be the part that you have shaded, and for a left-tailed test, that's going to be less than the critical value. Okay, so again, pretty much the same format as what you saw for Z. The t-curve is just a little bit wider, so the values will be pushed out a little bit more. And so you're going to be reading a t-table to find those values rather than the standard normal. All right, so just to make sure there's no confusion, we'll look at an example of each type. So a right-tailed test would be when the alternative hypothesis contains greater than, again, just like we saw for the z-test. For a right-tailed test, we would shade in the right tail of the curve. And then again, remember how the table works. So for left or right, you're always going to be looking up a one-tail alpha because it's all shaded on one side of the curve. So just like I did before, I'm going to look up a one-tail alpha at 0.05. And then degrees of freedom, we'll always take the sample size. In this case, I've got 14 values. And subtract from 1. And so pulling those two things together, I've got a value in my table of 1.771. And then again, you know about the sign. For a right-tailed test, you will have a positive critical value, so I can take it just as it is in the table for this right-tailed test. All right, and again, just clarification, critical value would be the 1.771. The rejection region, what is shaded, would be anything greater than 1.771. All right, and then we know our third case is when the alternative hypothesis contains greater than. Not greater than. When the alternative hypothesis contains not equal to, that is our two-tailed test. So again, we remember from Z, when that happens, we have a rejection region that's split, half on the left side and half on the right side. In this one case, right, because our rejection region is split, we will look this up as a two-tail level of significance. So just for the two-tailed test, will you come down here to this bottom row? Notice though, because this has a two-tail alpha, there is no need to divide by 2. So you won't do any kind of recalculating with the level of significance like you had to do for Z. You'll look it up exactly as it is. You will just be specifying if it is one or two-tail. All right, and then once again, I'm going to go degrees of freedom, 1 less than the sample size. So in this case, we'll have 15 degrees of freedom, and that's going to correspond to a value of 2.947. Again, we know from looking at this with Z that in a two-tailed test, we have both a negative critical value and a positive critical value. So once again, critical values would be negative 2.947 and positive 2.947. And rejection region, what is shaded, would be anything less than negative 2.947 or anything greater than positive 2.947. Now, like I said, this is going to be the only place that you see a change in how the hypothesis test is run. Everything else will be done exactly the same in terms of the 5 steps, in terms of how you make the decision, in terms of how you interpret that decision. So this difference will only occur in finding the rejection region and the critical values, and it will only happen when you need to switch to a t-test.